So now let's talk about work again. In physics, work is defined as a force acting over a certain distance. For example, d. If you were to consider a work being done, you have to take an object and you have to move it through a certain distance. So now what about work in terms of rotation? Well, the work in terms of rotation has a similar concept. It is now going to be a torque, which is a force, acting over an angle. So if you were to consider this is basically saying is if I have an object here, the amount of work that it's going to take me to move that thing over a certain angle as it goes around in a circle. That is what work means in terms of rotation. So work done by torque, by definition, is given by torque times delta theta, because delta theta is the angle or the distance through which the object moves. However, be very careful in noting that this angle is not considered to be in degrees, but rather in radians. So again, going over a little bit of math. So work done is given by F dot D, which is FD cosine theta. For a wheel, the work done by torque is going to be given by F dot D, which is equals to F tangential, which basically means is these forces acting on it, times R theta, and to be finally given by F and R. Fr equals theta, and so therefore the work done will be equals to torque times delta theta. Also, in terms of power we know is the work done per unit time. So if I was to put the work into this expression right here, torque delta theta, what I will see is another way of writing work in terms of omega, which is the angular velocity. Work is equals to torque times the angular velocity through which the object moves. So now let's do a problem. A flywheel of mass 182 kilograms has a radius of 0.62 meters. Assume flywheel is a hoop, something similar to this picture here. What is the torque required to bring the flywheel from rest to a speed of 120 RPMs, which basically means revolutions per minute, in an interval of 30 seconds? How much work is done in this 30-second period? So in this question, they give us a flywheel with a mass of 182 kilograms, and they give us the radius of the flywheel to be 0.62 meters, right? In part A, they say, what is the torque required to bring the flywheel from rest to a speed of 120 RPMs, which is revolutions per minute, in an interval of 30 seconds. So let's look at part A. Okay, so then it says that we are looking for what is the torque required to bring whatever object we have from omega naught equals 0 to V final or omega final of 120 RPMs, which is revolutions per minute. And it says in the interval t equals 30 seconds. Now there's a couple of things that we need to be very aware of. This is revolutions per minute. Now the two things that are wrong with it is we don't deal with revolutions and we don't deal with minutes. So we have to convert it into the units that we actually recognize, like radians per second. So how do we convert revolutions per minute into radians per second? Well, the first thing we need to do is we know that 2 pi radians equals 1 revolution, right? So that will get rid of my revolution. And then I also know that I need to get rid of the minute. So 1 minute is equals to, so recognize what I just did was wrong. Okay, so it's revolutions per minute. So in other words, I have to write this as revolutions per minute. Okay, so this means my 1 minute has to come on the top because I need to get rid of it. So this is going to be 60 seconds. Now these are the kind of mistakes that everybody makes, so just be very, very careful and cautious when you do that. So in this case, revolutions is going to go away, minutes is going to go away, and I can multiply 120 with 2 pi, and I'm going to get my answer in radians per second. So the answer is going to be equals to 12.6 radians per second. Okay, that's the number we're going to use. Okay, now coming back to the original question, I need to find torque. What do I know about torque? Well, I know torque equals R times F, right? Where R is the radius and F is the force applied. In this case, the force is going to be mass times acceleration, okay? So this means this has to be equals to R times MA, okay? This is a cross product. In order to get rid of the cross product, I have to include the angle between R and the force, which is 90 degrees. Sine of 90 is 1. So that means my torque, I'm just going to rewrite it over here. My torque is now going to be R. Oh, now it's going to be a magnitude because I've just changed it. MA sine 90 degrees. Sine 90 is equals to 1. So my torque is equals to RMA. Okay, now in this case, I don't have an A, but I do know that since the flywheel is going around in a circle, I have an alpha. So the relationship between A, which is the linear acceleration, and the angular acceleration, which is alpha, is A equals R alpha, right? So I'm going to plug that value into here. So my torque implies that my torque is going to become R squared M alpha. Okay? And alpha, further, I know is equals to d omega over dt. Okay? Change in omega over change in time. In other words, I can also write it as d omega over dt. Okay? Where I know what the change in omega is. This is going to be my change in omega. So this change is going to be omega final minus omega initial divided by delta t. Do I have values for these? Absolutely. So what I'm going to do is I'm going to plug these values in here, and my final torque is going to become R squared M omega F minus omega naught divided by delta t. Once I have that, I have delta t, which is 30 seconds. I have omega f, which is now 12.6 radians per second. I have omega naught, which is 0. They give me the mass and they give me the radius. So all I have to do is plug all of these numbers in, and I'm going to leave that up to you and actually give you just the final answer, which is going to be 29.4 Newton meters. Okay? And that is going to be the value of the torque that I was looking for. So notice in this example, we are using a lot of these equations that we already know, but that's kind of what we need to figure out. Whenever we look at a problem, we need to figure out, well, what is given, and what do I have, and what do I know, and how can I use it in order to come up with an explanation for my answer. Now for part B, it says how much work is done in this 30-second interval. In order to calculate how much work is done, I'm going to probably need torque again, so I'm going to rewrite this value, 29.4 Newton meters as my torque here, so we refer back to. Okay, so I'm going to get rid of this value for torque right here, and I'm going to think about what I actually know for part B from part A and from my prior information, because I need to calculate the work done. Okay, work done. So now this work done is because of torque, right? Torque is the causing force that's doing this work, and this torque causes my flywheel to move through a displacement delta theta. Okay, these are the two things I know. What else? Well, I know the value of torque, which is 29.4 that I calculated in part A, but I don't quite know what delta theta is. However, I do know that omega average is equals to the change in theta divided by the change in time. So this means the change in time is given to me, which is 30 seconds, and omega average I can calculate. Well, this is interesting. How do I calculate omega average? Simple. Omega 0 plus omega final divided by 2 will give me my angular velocity average times delta t will give me delta theta. Now all I have to do is replace this delta theta in here, and then my equation will be in terms of all the variables that I actually know about. Omega naught plus omega f divided by 2 delta theta, which is delta t. Now watch very carefully, right? So we know theta, which is 29.4 newtons per meter. We know omega naught is 0. We know omega final is 12.6 radians per second divided by 2, and we know delta theta is 30 seconds. Okay? Once we have all of these informations with us, all we have to do is plug it into our calculator and come up with an answer, and for me it comes out to be 5600 joules. Okay? But please make sure you do it for yourself in order for you to appreciate what all the steps are as we see them.